So what I want to do is continue first a little bit more with the kinetics of the theory of capital. So up to now, we've just done kinetics. What I want to do is start looking at kinematics. I said kinetics, I meant kinematics. All right, we've just been talking about the kinematics, and I want to, in this presentation, add the kinetics to get the full dynamics. And but before I do, I want to talk a little bit more about this business here, how you can look at that. So we've talked at length about inelastic capital. That's very intuitive how that works. Then we talked quite a bit about exponential growth. Well, that's also something with money and other things. It's quite intuitive, and we could see how we could generalize that and get this and that, all right? But this is nevertheless the most common in engineering as a rotational analog. And I did very little to make the connection with economics. So I want to do that first. And that's some background work I want to do because I'm going to draw on that when I do the kinetics, okay? So I'm going to give two more applications of this thing. Now, the first thing I want you to realize, if you compare this to this or that, then this kind of circular motion, what we call amortization, all right, it's symmetric in terms of a quarter-degree turn. So you can switch the chicken with the eggs and kind of get the same picture, okay? You can't do that here. If you switch it, it's going to go that way, all right? It's not going to look the same. And here you can't switch it either, all right? So you get a very different hyperbola. It goes like this, okay? So there's something special going on here. And if you look closely at this, so here you can really identify which must be the capital, and here which must be the capital, you know, and which must be the return, okay? Or the resources, I'd say, rather than capital. Capital, I think, is the radius, and here you can't. So what's going on? And what's going on is that you can take here, if you have a chicken farm, you can take two perspectives, okay? You can say, well, the chicken, they're my resource, and they're laying these eggs, and I'm selling these eggs, and my business is an egg business, all right? Or you can sell the chickens for chicken meat or something, chicken wings, I don't know, people eat that. And then the eggs is your resource because they hatch and they turn into chicken, okay? So if you have cows, you can be a cow farmer, and you know what? And these cows you have them running around. They become calves, and then these calves, you know, they are your product, and you sell that off. But another person, he may buy these calves, and that's actually what happened here in Delft on the what was it, the Beestenmarkt. You would buy the calves and then fatten them up, and then sell them as your product. Okay, so it's a little bit unclear here what you could use. You could take either perspective, and that's exactly right. Okay, so that doesn't mean necessarily that this for a particular person isn't his capital, his resource, or this is his resource. It just means you can take either perspective, which we also know is the case in reality. Okay, now to make that a little bit clearer, I want to. If you can do that, all right, so I actually went a little bit ahead of myself because this I did here. So let's do this one first, and then I'll come back to the other one, all right? Now, what you see here is another application of this amortizing things, but it's really not amortizing. It's called the production possibilities frontiers, and it comes from economics, and it's one of those things that economists use as one of the unifying examples that they will teach students, because it contains a lot of the concepts that are used in economics in one little figure. So a production possibility frontier, and is a famous thing, and this is a famous example. You have a society, and it can either produce butter or it can produce guns, all right? Guns are necessary to wage war, and butter is necessary for eating. It's a famous example. It's also in Wikipedia. I think it came out of World War II. I think it was actually the Germans who were proposing this, and they were saying, okay, we gotta, I don't know, there's a whole story with it, but this is the example. They say, all right, so a society has certain types of resources. And with these resources, they can produce so much butter, or if they apply all their resources producing guns, they can produce so many guns, all right? And they can also say, all right, in the middle, we're going to produce some butter and we produce some guns. And then you'll see that there is some kind of optimum, right? So here you can obviously the sum of the amounts are not equal, right? So if you are here, you're producing so many guns, and then if you don't get rid of all your butter, you'll only get a small amount of, that's what they call the opportunity cost, okay? So this is a kind of weird, this is not really amortizing thing. It's like a retooling of your industry kind of motion, you see? But it still makes a kind of circular motion, all right? Then they'll look at the tangent line of these motions, so that's our angular velocity, or at least the velocity that comes in, and they give a name to that. They call that the marginal rate of transformation. Why? Well, that is how much butter you have to give up producing to get a unit of guns, right? So it's just a tangent vector, okay? So typically, so you see, characteristically, they don't tell you how big this velocity is. So they're always looking at static things. But at least they'll tell you what the angle is. All right? Okay? And that angle is called the marginal rate of transformation. So I gave this is our normal thing for the yield. And I just made it a unit vector. You know? So the unit vector just tells you what the direction is. So I'm just matching here what happens, okay? Now, what they also will argue is that when a society expands, you go on a big higher or this is what happens. So here you have your production possibility frontier. You do an expansion, and you're now here, and in sum total, you can produce way more butter and way more guns. All right. So this is what they would call economic growth. All right, the expansion of the production possibility frontier, okay? So if we use our polar coordinate, this just, I'm missing the latex messed up here. So this should have been, ddt of the log of Q0, and that's equal to that, okay? This is how we defined it, I believe. Here. Okay? That's the expansion rate and the growth. Okay? So that's one reason why I call that growth. Okay?
You draw them all as corporate circles, but they don't have to be circles, right? They can
yeah, they can be ellipses or something. I want to come back to that business later. It's just that I turn it around a little bit here. I wanted to do an ellipse. Huh? Okay. But this is just from Wikipedia. They draw it as a circle. Yeah. So typically that's what you will do. And then you'll say, you know, it can have some kind of other shape. It can have a weird shape like this, you know. But then you're into this Lie group theory. I just want to stay away from it. I just want to look at some simple shapes, right? Huh? But, you know, like last lecture, we had this long discussion that you could have basically any shape, and you can sort out what the exact thing is, okay? So one way of looking at this is to say, well, I'm not even going to think of this as capital or this is capital. I'm going to think of these just as goods that are being produced. And I have a new type of capital, and that kind of is this radius here, right? Huh? Okay. And that's what they call the resources. So that's what I plotted here, right? So here is, say, the guns. Oh, this is the butter, Q1, butter. Here are the guns, huh? And then this is the, the resources that are available to society. And then you can imagine that you have this kind of cone. You fix the resources, and you slice the cone, right? So this cone, slice the cone like this. All right, you can get your proton, okay? So they will just move it around like that. But what we would prefer to do is add an extra axis for to measure the resources available. All right. So what does this example show? And well, first of all, it shows that you're not limited to 2 dimensions. You can do something in 3 or more. Okay. And it also shows that this kind of circular motion can correspond to other important things. Okay. So later you see what they will do is they will start retooling this. And in order to get this over here to there, you'll have to apply a torque, of course. So here it's going to be seen that in economics is no different. You have to apply some kind of incentive to the industry to retool itself, So the military complex may have to give, high prices for guns to make them produce more guns, all right? For instance, when they do that, they will provide the incentive and everything will start retooling and you can get some dynamic effects. We'll look at that later, all right? What I want you to see now is just how flexible these kind of setups are and how you can play with it. And as soon as you see some shapes like this, you can start thinking about how would you model this, and all right? Is that clear? So you can look it up. I mean, I just plug some stuff. They have all kinds of other things like, but we'll talk about this later. They call this the unbiased expansion rate because they could also have an expansion rate that is biased like this, so you're expanding more in this and you get different shapes. And then if you rescale, it will be, I don't know. Huh? That's why it says unbiased. They got all kinds of stuff, So this will be that marginal. So I just kind of drew it here. Okay? All right, let's go back to this other slide. So here I worked out what happens when you don't have a circular shape, an elliptical shape. Now, one of the things that you will see if you look at, let's look at these resources and their return. So if you look at crops, they come in, say, so many kilograms of certain crops. And the yield will be then kilograms per hectares over per year, all right? Because the land is measured in hectares. Now, what people do is they actually try to measure this and this in the same units. So in the agricultural industry, there is an agronomics or something, some kind of, you can look it up in Wikipedia. They have something called the seed multiplication ratio, if I'm not mistaken. And then what you do is you sort out if these are seeds, kilograms of seeds, okay, then you sort out how many seeds are needed to plant a hectare of land, and that number you use as a seed equivalent for a hectare, you see? So this will be also in seeds, And then this thing will become dimensionless, and your yield will just be 1% per year, okay? And this is how they actually do this. You'll see that if you take securities or money, this is automatic, right? Because securities cost money and they yield money, and then the whole thing cancels out, okay? So economists always try to get rid of units, and for good reason. We do that too, right? Huh? And here you see just people in general do this, okay? That makes a lot of sense. Okay, so let's go back to this slide here. So here I had so that's the seed multiplication ratio. Now, if you draw, if you this one, you'll see the seed multiplication ratio. So if you draw this thing, if it's not a circular shape but an ellipse, what happens is you have these two axes. They're not the same, right? So there's no single. There's some kind of weird radius. Okay, I don't know yet what it is. Right? I'll show you later what I think it might be, your capital, but in principle, you have this thing called the semi-minor axis and the semi-major axis, all right? So I'm saying here that the seed ratio, the land is less seeds than the crop, right? That's very typical. I think in Europe, in the Middle Ages, it was what, like 2.4 or something. With one big exception, there was the Netherlands, apparently. I looked this up. And in the Middle Ages, they had a seed ratio of 14. So it's extremely efficient already in 1500, all right? Which explains a lot of the wealth of this country. So they're able to feed these, there's a very small amount of land at that time with some big trading towns like Amsterdam and maybe also Delft, but Middelburg and those things, but especially Amsterdam. A very small amount of land was able to feed all these people because this reseed ratio was so high. Actually, Louis XIV, who had eternal wars with, I read this, it's pretty interesting, who had eternal wars with Holland, as you might know, right? Huh? He complained about this because that the productivity of the Dutch farmer was so much higher than in France, so they just kept being able to feed their soldiers and everything, right? So, and still it's the case, I think. We are able to be a big exporter of agricultural products, right? Because the seed ratio or flower replant ratio, with flowers we do it, right? Okay. Anyway, you can see by the ratio of this semi-major axis and semi-minor axis, this gives you the seed multiplication ratio, right? Do you see that? Okay, do you see that? That's clear, right? So then you go through this kind of elliptical motion. So you can see how much you have in stock and how much you invested in, is stuck in the land, huh? All right. That's this and this. They correspond to these. So the maximal amount you got to do in here is this, what you have to invest. So that's what you got to plant. And this is your maximum stock amount. Now you can find out what is this R? Well, really, if you have an ellipse, you have these two foci, right? And then if you have any point like this, you would draw this, and you'll take the sum to be equal, right? But you never get to a sort of radius that can serve as a measure of how much capital is there. So what you typically do is to look at what circle would have the equivalent area. I will see later why that is a good choice, because you will see that the price goes by how much area is being swept out. As you know, the angular momentum is like that, all right? So you can find out that if you do that, you can take this geometric average of the two, your investment and your stock, and then that's your equivalent capital, as it were, and that's called the equivalent radius. This is called the aspect ratio. There's a whole bunch of stuff with ellipses, like eccentricity and this and that. And I bet you they all have good economic equivalents, but it'll be fun for somebody who's interested in that to figure out. Again, all I'm trying to do here is show you how you can get some shape like this and give it a very compelling thing. Here I put some other things. I also added something with, if this were money, your credit cycle. So you see, if you have some kind of investment, or some loan, and you receive interest on it, then maybe the interest is then lower, right? And this sort of will be like that. Huh? But you can keep track of how much principal you have, how much interest. Here you keep track of how much you planted and how much you have in stock, all right? When this velocity is 1, is bigger than 0, you're harvesting. So here you're harvesting. This is the fall. And here you must be planting, right? So it goes down. You know, you can just... Again, that's more to your question, like, can this have any shape? And this is a simple shape you can have. So if you work your way through it, you'll see all kinds of shapes coming up. It usually is, it behooves you to take a simple shape for your analysis, right? I mean, that's close enough. And then, then you work with that. And then any weird stuff, you just, you know, if it's interesting, you can develop a lot of math. Okay? So here's 2 more applications of this idea of how circular motions come into... circular motions are important, right? So one of the things why we always assume in mechanics is that our space is invariant under circular motion. So you can take something and just rotate it, okay? And in economics, you can't assume that. But if you have an ellipse or a circle, then you can, right? Because they are invariant in the sense that you're the same farmer, you're just somewhere else on this cycle. It doesn't really matter, all right? And this phase difference is not gonna make an important thing. So there's this symmetry, all right? And that symmetry corresponds to the same symmetry as our own space, because then we can use Euclidean distance to measure everything, and then everything kind of feels right when you draw it, all right? So if you use a different kind of space, like a hyperbolic space, it all feels kind of weird, you know? You see, like, how come this length is equal to that length, right? But here, you know, here it all works out, you know? Okay? So our intuition is really good for these things, all right? So I wanted to get that done with. And with that done, we have enough to start talking about price, all right? So our whole premise is that the way to find the price, remember, I showed you that way back in the beginning, when we have price for commodities, they're just going in along a line, right, along an account. That the way you can get at this is by requiring that the description is invariant on the shifts along the account. It doesn't really matter how much apples you already ate. It doesn't determine, you know, how much you're going to demand, all right? If you look at the theory of demand, for instance, okay? So price came out of an invariance under this transformation group. We call them groups of transformation. So all the translations, if you put them together, we call that a group, okay? Now, we're going to apply the same trick here, except now we don't have translations, because if you take this thing and translate it, it's not going to be the same, right? This thing's not going to be the same either, right? And, you know, you translate it like this, it'll be the same. That's exactly the only one. So that's the only commodity you have is going in this direction, okay? And this one, you can't do anything with it either, you know? So how is this thing the same? Not when you translate it, but when you rotate it, it's just the same, okay? So what you need to do is to look and see under these rotations, what is this quantity that remains the same, okay? And if you have that, then you know, huh? You're in business. Then you have something that you can call price. This is how momentum is defined, right? So it's the thing that remains the same when you make these allowable transformations, okay? So if something has momentum and you just move the space somewhere over, it's not going to change the momentum. But if you rotate the space and it's got linear momentum, it will change. All of a sudden, the momentum will go in a different direction, right? So linear momentum is not invariant under rotations. Now, this is a famous problem, okay? Finding what momentum is. And it was, the conclusion was drawn by Newton, but the right idea came from a guy called Kepler. I'm sure you guys have heard of Kepler, huh? So why did he get famous? Well, because he described how the planets move around the sun, right? So I didn't know how they did that. They had all kinds of weird ideas. And then they plotted some stuff. They had thousands of years of data. The guy is just amazing how much data he had. And then somehow in this data, he realized that, that the area that the thing sweeps out in a unit of time, right? This is the area he draw, right? Remains constant, okay? So in a circle, that's definitely the case, okay? You can see that, right? So here you have some kind of speed that it's taking, right? And this is the area, and here another one is the same area, obviously. But in an ellipse, it's going to be slightly different, right? So here you have some kind of area. Let me go to this one. No, that's a hyperbola. Let's go to this thing. So here you'll have an area. But here, you'll also have an area. So, but this thing has to be shorter, right? In order to get this area to be the same as that area. So you can't have these things of equal length. They go slower, right? So it's a mistake to think that this body is going at a constant speed, along its trajectory. Only if it's a circle will it do that, right? So you have these planets, and they kind of slow down when they are far away from you, and then they speed up when they come closer to you, and then they slow down. But for the planet, he's just going at constant speed. From your perspective, he is, all right? So the planet is in equilibrium, okay? So there's nothing is slowing him down, actively slowing him down, all right? So what's actually happening, then the Kepler noticed it, is that this area is the thing that remains constant, not the speed, okay? In Dutch, we call it the perkewet van Kepler. And in English, this is called Kepler's whatever law, second law, first law, I can't really remember. But it's, this thing is called the sectorial velocity. Sectorial velocity. Because this is like a sector, right? And the rate at which the sector changes, right? That's what this is. As you take the velocity, that's a constant, okay? So that's our candidate, all right? Now, the thing that Newton did, he says, well, that's very nice and well, Mr. Kepler, but you shouldn't have taken the sectorial velocity. You should you should have taken the momentum, m times that sectorial velocity. That velocity of the tip, sorry, not the that's okay. It's the same as the sectorial velocity multiplied by m, right? So that's you should have taken this vector to be the momentum, right? So for us, that means that instead of the quantity demanded, we have to take the price here. So it's the price of the eggs, say, all right, that we're taking to value these chickens here, okay? It's the momentum in the Q1 direction. These were the eggs, right? Okay? So the momentum in the Q1 direction is the price of the eggs, okay? But we're multiplying it by the amount of chickens we have, all right? Okay? And then the other thing Newton says, well, you took half of this. What I think it should have done was do P times this number R, the radius. So get rid of a half, right? So you really should have calculated this area. Okay? All makes no difference. All constants. All right? That's what Newton did. And I believe that's Newton. Huh? Sometimes I get confused what Euler did and what Newton did. I believe Newton did this because he solved it in his Principia, how the planets move and how Kepler's laws can be predicted. You see, this was the issue. Kepler, he was like an economist. He had fit the data really well, right? But he had no law predicting this, okay? Every new planet, he would have to like take a gazillion data and try to fit some kind of ellipse. And then if he had a thing coming by with a hyperbola, he wouldn't know what it was because he would spend way too little time and it'll never come back, right? So if it's not in orbit, he didn't know what to do with it, right? Huh? So you can see there's a big difference here. There's fitting data and getting the law, right? So Newton comes up with the law, all right? Huh? And then he shows that the law explains the data of Kepler. There's a famous story is that people couldn't believe it, right? So they had this one planet that is going like this, and it did everything just fine, except there was a bubble here, you know, huh? So they said, hey, your law is wrong because look at that, right? There's a problem, right? So then you know what happens? Some other guy says, well, maybe that thing got there because I think it was like this, actually. Huh? Doesn't matter, right? There's another planet over here, and it's just coming a little bit in the orbit of that planet, right? And that's why you get this deviation. So he applied Newton's law to this like three-body problem. It's kind of a complicated problem. And he figured out that where that planet should be in order to, in order to explain this. But then they saw that you don't really see this planet. It's always kind of hidden somewhere. I don't know, the wrong side of the Earth, I don't know. But at a certain point in time, you could figure out that if it were there, you could see it. And they went to look, and there it was. So when that happens, you know you're in business, okay? All right? So you know the data fitting is over now, okay? You know that's gone, all right? Now we're just finding out where the planets are and solving an equation. So this is what you've got to see we're doing here, all right? So you do your data fitting, you find that these things go in a business cycle, or I do this cycle and this, and then you find something that's not working right. Don't declare the theory to be wrong. No, stick with your theory and say, well, maybe there's another effect, and I got to model that, right? All right, and then you find the other effect. You see, you got to make the leap, okay? Because there were a lot of doubters in those Newton's day. They said, this can't be right. That's ridiculous. Why would this simple law do everything? How many thousands of years have we been working on this? You know, it's crazy. Huh? He doesn't know what he's talking about. Because there's people with academic jobs who made their careers out of doing this data fitting. They're not going to go away, without a, with the celebration. No, they're going to go like, no, we know what we're doing. Right? Okay? But stick with your guns. Okay? It's another way of thinking, and it shows you the power of this kind of stuff. Okay? So what is now the price that's going to stay? Well, we're going to R, and we're going to multiply the price of the produce times the amount of capital that we have. All right? Okay? If you work it out, you know that this is M times V, and then you get this expression, right? So this is the yield. This is the price. And this is sort of like a new mass, right? This is what we call the moment of inertia. We'll talk about this. And it relates the yield to the price of the land. So this is the price of the whole business, not the land and all it produces, okay? This formula is valid for all cases, right? You just have to get the right definition of R in there, and you're done, right? That's the trick with this thing, right? Huh? So you first have to define your capital, and then you're done. Just fill in the equation. It works for all of them. All right? So this is the price of this capital you have, right? Your business, your farm, I don't know what. This is what we suggest as the price. And when that price doesn't change, that's the case that this thing is going at a constant speed, and that's the case where we have these Lie groups theory and we just use the exponential map and we go out, all right? We are in a sort of price equilibrium, right? Because now the price doesn't change. This is what economists always look at. We can look at price changes, and that's exactly what I want to do with the kinetic part, okay? All right? So here, just like momentum is the price for the commodity trades, linear momentum is linear accounts, those are commodity accounts. So angular momentum is the price for capital, all right? Capital accounts. Now what's weird about this is that this price is the price of this is the resource, R, and this P here, that's the product. So you're somehow multiplying these two. Why does that make sense economically? I mean, you're so used to seeing this in mechanics for angular momentum. Of course you do that. That's the arm, and there's the momentum here, and chaka, right? Huh? But why does that make sense? All right. On my next slide, I want to talk about this. All right. And I got a bunch of quotes. I'll go through them. But this thing has a big, big history, because people could figure out what the price of some commodity is, the price of apples or the price of, bananas, I think up to, maybe up to 1800 or something. Yeah, I would say up to Ricardo. But why did land have value, right? That was not so clear, because you couldn't really eat it, right? Huh? Why does a house have value? You can't eat that either, right? Huh? Why does it have value? So there was this guy, Ricardo, he came up with the solution. He says it has value only because you can produce stuff with it, okay? Otherwise, it has no value. So when the European immigrants came to North America, the native population wasn't using the land to produce stuff with it. Therefore, it had no value, right? You could just take it. They don't care, right? Because they really were more hunter-gatherers than they were farming types. So they don't care. Here, worthless. You can take the air too. Go ahead and breathe it, right? Huh? You get a bag of beads for it, and they go, yeah, a good deal, right? So nice and, So they did a good deal in their eyes, all right? They calculate, though, that if you had invested those, the proceeds of those beads on the stock exchange and waited, it would have been worth more than the land is worth now in Manhattan. So it was a good deal, except they didn't invest it. Right? So this is what Ricardo says. So he writes this down in a book, The Principles of Political Economy and Taxation. So everybody's interested in how to tax you, right? And how to tax the land, right? So he came up with this idea, let's go, corn is not high because a rent is paid, but a rent is paid because corn is high. For the old guys, rent was the payments you made for the use of the land. They call that rent. It still is kind of rent. Huh? So you rent the land, or you rent a car, or you rent something. Those payments, that rent is high because corn is high, all right? And then rent is that portion of the produce of the earth which is paid to the landlord for the use of the original and indestructible powers of the soil. So the original indestructibility means it's an inelastic resource, right? The land, okay? Somebody owns that, right? This is this property ownership. This is the beginning of capitalism, that you can actually own this, right? And then you have the right to charge some price for another to use it, okay? So you see, if you then go back to this definition, this is good, right? So corn, the land is worth a lot because corn, and this is the price of corn, right, is high. Of course, you got to multiply by the amount of land you got, right? Because it's got to be proportional to that. Huh? Okay? This is precisely what this is saying. Do you guys see that? Okay? Now, the economists write big books about this, and there's all kinds of considerations. It's good to take a look at. But my feeling is this is correct. It has to be correct, because if the shape is like that, the only thing that will give you a good notional price equilibrium is the invariant quantity, and that must be momentum, or angular momentum. So, huh? All right. Okay. So something happened here, all right, that I want to have you guys sink in. I have another example from a different time, 1938. This I chose because it's right after the big stock market crash in the United States and the world over. Now, what was the problem there? So stocks were invented actually by the Dutch East India Company, and then they were traded, and there was no theory for doing that, all right? And you had these weird, even in the Netherlands, you had these weird bubbles. So you had a tulip bubble, because people somehow believed that tulips would be worth an enormous amount as an investment or something. And then in England afterwards, you can look that up, there was something called the South Sea bubble. And actually Newton lost his fortune on the South Sea, speculating on the South Sea bubble, I believe. He was bankrupt and he was so angry. So the poor man, he could predict everything, but he couldn't predict the stock market. He got suckered in, right? It's an interesting story. Okay, so there were all these crazy things happening, where all of a sudden the stock of the British East India Company went through the roof, and everybody piled in, and all of a sudden it comes crashing down, and nobody really understands why or how, okay? And they talk about psychology and stuff, okay? But nobody had a good theory for this. Then in the United States, this business of trading shares in company really in New York got going in the end of the 19th century and the beginning of the 20th century, and it exploded in the 20s, all right? Stocks went through the roof, railroad stocks, this stocks, that stock, a little bit like the dot-com bubble in the 90s, and then later some other bubbles we've had. We also go from bubble to bubble, right? Okay? This went through the roof. And then all of a sudden, somebody started selling, and then the whole thing came crashing down. So one of the problems they were facing was that companies would just be able to print shares just like that. Just came out of nowhere, you print them, you float them, and people would buy them, right? So, what was it worth? Nobody knew. Wat de gekke vergeeft, as we say in Dutch, it's just demand and supply, people thought, for stocks. But they're pieces of paper. Why is there demand for a piece of paper, right? Okay, this is the question that wasn't answered. You just think it's demand and supply for the thing itself, but that was not the case. And there was this guy, John Burr Williams, and he kind of laid the foundations for this theory that you cannot look at the stock as a piece of paper that is just a consumption article for which there is demand and supply, and that's the price. That's the wrong way to do it, You have to look at the dividends the stock pays, okay? And when you own the stock, you really don't own anything except those dividends, all right? Okay, and maybe if you're lucky, well, that's all, right? Yeah, there's no maybe if you're lucky. You just own those dividends. That's what it is. And nowadays, companies don't like to pay out dividends because they get taxed high. So you look at the earnings, and they put the earnings in a separate retained earnings account. And as a shareholder, you have the right to the earnings. That's the idea, okay? But that company itself, who cares? Maybe there's some scrap value. But if you have an internet company like Google or something, there's no scrap value, maybe a few buildings or something, right? So it still has an enormous amount of value. So that can't be it, okay? It's all about the earnings, all right? And the way he said it, it's an old saying that he wrote in his book, a cow for a milk, right? A hen for an egg. So I call it a chicken, right? But we looked at that example, right? And a stock by heck for our dividends, okay? He says that's the only thing that matters, right? Just look at the earnings or the dividends. Then you know how much the stock is worth. We all know that now, all right? But they didn't then. And he goes on, an orchard for fruit, bees for their honey, and stocks besides for their dividends. So he does this rhetorical device that's called repetition, right? You just hammer it in, And this was his whole thesis, right? So what is, if I go back here, what is this? Well, this is the price for the dividends, how much you appreciate that stream of money. That may not be one-to-one, dollar for dollar, right? That can be whatever, how much you need the cash, or okay? And this is the amount of stock you own, all right? Okay? And if you multiply it out, you get the value of the stock, all right? Okay? So every time you have some notion of capital, it typically does not have value by itself. If you have chicken, it could, and it's a little bit, you can sell the chicken meat or you can have this. So you got to be a little bit careful. But if you have land, it certainly does it, okay? So there's only the angular momentum. If you immigrate somewhere, you could just grab a piece of land, it costs nothing, all right? But if you just grab it and that thing is already yielding, you can't just grab it because you'll have to, you'll whiplashed, you'll be slowed down because the thing is going at 0 speed and you can, all right, okay. So here I have that same table we had before. I made some modifications. I'm not quite sure why. Oh, because I like the units better. So what I have here is those different types of capital. And here, all I want to do is, I'll take TU blue. What I want to do is highlight the units for the price, okay? So if you work it out, you'll see what you need. Well, okay, there's different ways of working this out, but the way I always do it is I know what the units of the yield are, right? And I know that the price times the yield must be, it must be some kind of value flow, right? So if this is in I don't know, bushels hectare per year, then I know that the other one is so many euros per bushel hectare or something. All right, it's whatever this flow is. This flow you divide by the numerator, right? Because you need to get that product to be. All right. You can also take L multiplied by theta. That's the integral, and that has to be the units of your currency. Okay. So then you can figure this out. You can figure it out just by dividing and working through the formula. All right? Makes no difference. So here you see that if you have land, you're paying so many US dollars of per bushel per hectare. So what is this saying? Well, if you have reseed ratio, this thing is actually vanishes and you're paying so many dollars for the land, right? That's precisely what would what happened. Now, if you read Ricardo's theory, he has a thing where he goes on, and I didn't really read his book, but I read all the people who came later who are analyzing this, like Samuelson. It's just in those texts. And then he says, well, very fertile soil is worth more than non-fertile soil, and the most fertile soil is what now is worth the most, and that's what people first grab, and then blah 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 blah. Right? It's a complicated theory. So you can see here by these units that what you're really doing is paying per unit of productivity here. So many bushels per hectare. The thing is giving twice as many bushels of corn per hectare. All right, you're going to pay twice as much. All right? So that's what I like about these units. It immediately solves this whole problem of the productivity of the land and all of this. So this is a sort of a product, you're really buying productivity, okay? And the rate, the yield rate is productivity per unit of time, okay? Now, if you fix the reseed ratio, the productivity is fixed, and then you just pay so many dollars for it. But if the reseed ratio is different, you'll have to adjust this, okay? Yeah, because you need to have this thing to be invariant. If you make this one twice as big, this one has to be twice as small, right? Okay. For capital, it's the same thing. So you're making these products. These are a number of items. So you're paying also per efficiency, so many items per machine, right? Now, labor is interesting, right? So if you work through your way through it, you'll see that you're paying so many dollars per hour, all right? Because of the way, remember, these things, person hours, they cancel. So the productivity has no units. And then all right? This is exactly what you feel, right? The wages is so many dollars per hour. So you see the wage or the rent is really the price, okay? It feels weird why something per hour should be the price, but this is just the way it works out, okay? That's also what we do. This worker is worth so many dollars per hour, right? Housing is so many dollars per month. That's the rent. This is the rent that thing talks about, okay? That's what you pay, so many per month. Money, everything cancels and it's just in dollars, right? Which is what we know. So, I'll pay you $8 for every $10 of debt you have or something, right? Huh? Okay. And securities too. So it's kind of interesting to see how the units just kind of work out perfectly, but I wanted to show you that. So be careful, not everything is just has the same units. You gotta keep your head screwed on right here and go through the details, okay? But you'll see that if you do it right, everything will make sense. It's exactly how it happens. And if you make a mistake somewhere, none of the units make sense, and you won't have this, or the units come out. And so always check your units. Do what economists never do, right? Put units and then check them. All right? So something has happened here now. I convinced you about how to use economic engineering to price securities and land and other kind of things. And I'm trying to convince you this is also in line with how Ricardo and others viewed this, all right? Now, what they don't have is a theory for a kinetic theory. They don't know how to deal with price changes, right? But we do, right? So what I want to do now is formulate this law of demand, right? Now let me just ask you guys, how do you call the time derivative of angular momentum? What do you call the time derivative of regular momentum? Yeah, force, right? Oh, come on, right? Huh? Everybody knows that, right? Huh? No? You don't know after sometimes say, what's the matter with you guys? Huh? Just because you come here, you turn into Mickey Mouse, huh? So what's the rate of change? What is the rate of change of angular momentum? Huh? What?
So like the force
Yeah, it's a turning force. How do you call that? Torque! Jesus! Huh? Huh? You know, it's, well, you know this. Huh? Well, we're going to try to derive this thing, okay? But I already want to tell you, you guys are, now that we've done the hard work, you kind of already know everything. We've defined what we mean by price. You know price is angular momentum, and you know the entire kinetic theory that goes along with angular momentum. You get it in dynamics your first year, right? Mess around with all these equations, all right? Huh? You should know this by heart, okay? So this is what we're going to leverage now. We're in good shape. You can see that, right? Except now we'll be able to interpret everything economically. The moments of inertia, torques, the whole shebang and shaboodle, all right? Huh? Okay? So, first I want to, so that's what we're going to do here. First I'm going to write down the equivalent of P is, what am I going to do? Yeah, M times V, right? Huh? So that's just the Cartesian, the definition of regular linear momentum. So we want to replace this by our angular momentum, so that's our price of capital. We want to replace this by the yield, right? And then we're going to have something else here, and what does that correspond to in mechanics? Yeah, the moment of inertia, right? Huh? Okay. So you can kind of see what this moment of inertia is, right? So if I look at dl d omega, that is the moment of inertia, right? So it's the change in the price if I change the yield, right? Okay. That's called the yield sensitivity. Okay. Well, it seriously is, but you can see that makes a lot of sense. Okay. So how sensitive the price is to changes in the yield. You know it is, because if you have land and all of a sudden it starts yielding less, it's not gonna, the price will have to adjust, okay? All right? If you have a bond and all of a sudden it's paying less interest, you know, it's not worth that much, okay? And that's what was called the yield sensitivity, huh? Okay? I never know whether it's the inverse, that's the yield sensitivity, or this is it. Huh? Maybe it's the yield, I don't know, but this is good enough. I don't think anybody else takes that too seriously. Just, huh? Now, if I work this out, I can see, okay, so that, I'm going ahead a little bit. So let me just come to this. That was just getting everything we knew from mechanics and immediately doing it. But now let's build this up step by step. So this is the definition of our price. Huh? So you take the price of the products and you multiply it by your capital. All right. Now I know that this thing here is M times V. Huh? So I can write, if I define mu to be this, I can rewrite it like that, okay? Is that clear? I mean, listen, I just pulled an M out here, and I said M times R is mu, right? This is not too hard even for you guys, right? I always have to take a while. When I know it, I pretend that you guys are stupid, but it's not stupid. It takes a while. Especially the simple things are hard to understand. But if I give you a big formula, you will just go, oh, yeah, no problem. I have something really simple. You go like, oh, shoot. Huh? Okay? Now, this thing, I use the word mu because economists call this the multiplier. Okay? So suppose you have some stock, and these V is then the earnings, right? So that's what the stock is yielding. they will call this the earnings multiplier, because if you take the earnings and multiply by that, you get the price of the stock. Sometimes they call it the price-earnings ratio, and it kind of is, right? So you can define mu to be L over V. So these are the earnings, huh? And this is the price. Huh? Okay? So literally is, it not kind of is. Huh? You can have people with investments, they call it the capitalization rate, or they always talk about a cap rate. It's the same thing, okay? P ratio, there's a ton of names. Earnings multiple, everybody has got their own favorite name. All right? This is what economists use. Now, why, I mean, do we ever use this quantity M times R? I think not, right? You don't learn this as a special concept. Now, why do you think that is the case? It's a subtle issue, but the problem is what you always want is that the price times the flow is in dollars per year, right? Huh? Otherwise, they're not conjugate, you know? They just don't really belong to each other. So if I take this and multiply it by V, I'm not going to get that, okay? So I need to multiply this to know that these are matched, okay? This is what we call in mechanics conjugate variables. So you can't just use one type of momentum and another type of velocity. I can't use angular momentum and then and multiply that by linear velocity, you see? Huh? Okay? I have to multiply angular momentum by an angular velocity in order to get, you know, if I calculate kinetic energy or something. Okay? Huh? So that's why we don't do it, because they don't match up. We say they're not conjugate. Okay? So L and V are not conjugate. They don't belong to each other. So that's why we don't use it. So most people on the stock market, they don't really care because they don't really do this multiplication and they do nothing. It's just a nice way of keeping track of it, right? But you got to be careful when you do this kind of stuff. So you can use it, but what better to do is to rewrite this as R times omega, okay? The actual crops at which they're going, the commodity, you write it like this. And then you'll get this new thing, I, when you multiply another time by your capital, and you get MR squared, right? Huh? And that thing is the real yield sensitivity, right? Huh? Okay? So price of capital is related to the returns, not to the actual flow of the commodity, okay? Of course, this is easy to do here, so you should just do the relative earnings here, right? And then you will see that you'll get the right thing. So as long as you measure the earnings not in dollars per year, but in percent as a return on the investment, then this thing will work, okay? So I want to alert you with this. So you see a lot of stuff that's out there is coming together here. There's a lot more. It's called the yield system, but they have tons of names, all dependent on whether they are buying land or this or that or such or so. Okay? The fit is really well. I want you to realize that. Okay? So it takes a while to see all the little things, but the fit is really well. See, in the end, the good thing about this is, say you're building your model and you're using SPICE or whatever, or you have a bond graph, you just put in an I element, and you don't really care whether it's some capital, but this is rotational, and you have an omega here, and then some torque over here, right? Or whether this is a flow, and this is just a flow with your effort, and you're done, right? So you have to think your way through the theory, but then when you build your models, you're in good shape. You know, now you can treat it just like any other linear element. You just got to get your circuit programmed right, you know? Yeah? That's why I'm doing this. Okay. All right. Now we want to see what this torque is, okay? So we talked about the force of demand. Now we would have to talk about the torque of demand. It sounds a little funny, but I think it's okay, you know? It's some kind of desire, but it's a desire for yield, right, or returns, you know, not a desire for the actual product. So rather than saying, okay, I want these apples, you're saying, no, I want something that gives me a lot of profits, you know? So it's a desire to get returns, you know? We all, it's the profit motive. This, you can think of this, I mean, that's a nice way to look at this. Think of this as the profit motive, huh? So profits you make on investments, you know, huh? Yeah, it's, huh? Okay. A motive is the same as a force, huh? You have the motive force. Newton called it the motive force. That's all done before. So you can think of this as a sort of a profit motive. So people not only have a motive to buy consumption goods, but they also have a motive to buy things that will yield consumption goods, okay? And that's a torque.
Similar to incentives in commodities?
What?
Similar to incentives in commodities?
Yeah, of course. I mean, a torque is to an angular velocity what a profit motive is to a, huh? Yeah. All right. So let's continue. Where are we? We have this thing that we can call the torque of demand, or in general, something we might call the profit motive. Huh? Some kind of business motive, some motive you have to go and run this business. All right. And then you can look at the change of these yields. All right. And that's when yields are going up, or when yields are rising, or yields are going down, or whether they're being hiked up. It happens all the time, right? The central bank may do that, or you may increase the fertility of your business, your soil through means. That's what the Dutch did, etc. Okay, so that's the angular acceleration, right? There's no good name for it, you know, except I looked it up, and people just talked about rising rates and falling rates and rate hikes when it goes really fast, when it's high accelerations. And you just got to kind of fill it in. All right? I just want you to realize that this is the angular acceleration. Okay? And then you can calculate what this profit motive is. And if you go through the derivative, you'll see that if it consists of two terms. One is the acceleration times this yield sensitivity, and the other is the rate times the rate at which the yield sensitivity is changing, you know? This is the same as in the linear thing, where you have F is m times A, but there's also this term, right? For when the mass is changing, okay? Usually we'll assume that this is zero, right? This is zero, and then you just get your regular, you know, the torque is equal to the moment of inertia times this, all right? But it doesn't have to be, okay? Now, I don't know what I did here. Oh yeah, I just worked it out, right? So as opposed to the linear case, two things can happen. Actually, you can get more land, you can be expansionary, right? Huh? That's interesting, right? Huh? Or the price elasticity of the products can change, right? So if the price elasticity of the products change, you got some adjustments to make there as well, right? So that's called a rotation of the demand curve for the products that will give you a change in your yield sensitivity, okay? With this, we're going far beyond anything economists have done, you see. This is the great thing of having this kind of theory. You just take the derivative. I just chain ruled my way through this. I only forgot that I did it, but it's simple, right? Okay? Huh? Well, this thing we know, you know, how do you know this? There's a famous thing that happens in ballet and stuff. Huh? Yeah, I know. Okay, but what's the phenomenon where you can see this happening? Yeah. So you have these skaters, right? And then they start turning, and they turn like this, and then they pull in their arms, right? So this thing, this thing gets reduced, and because of the price will have to, then the momentum has to be conserved. She starts spinning like much faster, and then you're slowly out and then coming in. Okay, huh? All right, huh? So you see that this effect is the same as the expansionary or contractionary effects that you can make with your land, right? So you can model all of those figure skaters, okay? This effect you see when people are balancing wheels, right? So there's a wobble in it, you add some, well, not balancing wheels, you put more weight at on the outer rim of, you add a weight at the outer rim, and then you'll see that the momentum slows down, So you're turning and then you grab something, okay? Or you throw something away and then, okay? So the same thing you see. This is an interesting effect, right? When you're doing some deposits or you're doing an investment, you'll see that you'll get all these type of funky effects. It's very interesting, okay? So I drew this here in this kind of, so you get the same kind of demand graph that you had in the old days, right? So you know how here's the economists, they put price, and here they put, the quantity demanded. Here, this is the demand for yield. Here is the price of the resources, and you get these things, and you get a rotation and all this stuff, okay? So this is just the law of demand, but now it's not demand for products, but for yield or return or profits or rates of profit, okay? This is my last slide. So I wanted to apply this to a simple case. I'm going to take something from banking. So in banking, you have these two types of accounts, right? You can have these savings accounts, and they pay interest and they compound, right? So the interest gets put back in the account and the amount grows, and then you can plot it like this. We talked about that, okay? This compounding and compound interest. So here's the current balance, and here is the interest receipts. Or you could take a mortgage, and then you start off with this loan, and then you start making interest payments, but you also have to make a small repayment of the mortgage, and you go around in these circles, okay? Now but nobody is saying you have to go at a constant rate here, So what is determining, how fast you're going, how fast is, nobody is saying the interest rates on these accounts have to be always the same, They keep adjusting them at the bank. And all of a sudden they say interest rate is lower or higher, right? And where does that come from? So when you change the interest rate, of course, that's some kind of acceleration, right? Okay. And that acceleration, how do you get an acceleration? It doesn't come from anywhere, nowhere. It has to come from a torque, okay, an angular acceleration. So you need to have some kind of torque. So here I wrote it down. So these price, the price of this asset, now the change must be this torque, okay? So, and we know that that is linearly related to the rate at which the interest rate is changing. Okay. Now, if you know that the change in the interest rates is this, then that must be equal to torque divided by I. So how do I find the omega? Well, I have to integrate this, and I just did that here. Okay. So all I did was integrate it to get the angular velocity from the torque that you apply. Okay? Nothing special. All right? It's just a very simple formula. So the torque gives you the angular velocity, angular acceleration, and by integration, you can get the angular velocity. Here, the profit motive gives you the change in the price. The profit motive tells you how much the interest rates, it comes from outside. Somebody applies for, hey, I want this stuff, okay? And then this is the new set of interest rates. So in order for the bank to charge its interest rate, they have to incentivize you, this is the incentive that you have to, this is then the incentive you have to supply. Okay? Now, if I put that into place, I can go figure out, I don't know why this says Q, this should have been V1. I can figure out for this thing how, this is how much interest I'm receiving and how much the rate at which my capital is, my balance is increasing, okay, the interest and the balance, by just integrating this out and going through the geometry, okay? So you'll see that this is what you get. So this is the rate at which the principal goes, the interest goes, and you can sum them, that's your total money, and you'll see that you'll get this exponential growth, okay, of your total receipts. This is exactly what we know should happen. But this is not exponential growth. I actually should have done a little better job here because, well, no, that's okay. See, the problem is this is only true. I did a bad job, so I'll do this next week a little better. You can't just, only when it's constant does this happen, but if it's not constant, I have to integrate this omega over t, and I have to plug that in there. So I did a bad job here. All right, so I'll fix that for next week, okay? And then when it's constant, you get this expression, okay? And the same thing here, okay? So I'll fix this for next week, and then we'll keep going. So